Imagine a world where your most sensitive data is genuinely, truly unhackable,
Hmm.
or where doctors can peer inside living cells without causing even a tiny bit of damage.
Yeah, that's a big one.
Or, get this, where scientists can detect the absolute faintest whispers from the cosmos, ripples in space-time, with just unimaginable precision.
It sounds like science fiction, doesn't it?
It really does. But this isn't just some distant dream or a plot from a blockbuster movie. It's actually starting to become our reality thanks to this quiet revolution in how we understand and, well, use light.
That's exactly right. Today, we're taking a deep dive into this fascinating world of photonic quantum technologies.
Photonic quantum technologies.
Okay, these are really groundbreaking advancements that harness the unique, sometimes frankly weird, properties of individual particles of light photons to do things that are just way beyond what's possible with our current everyday tech.
So, our mission today in this deep dive is to unpack the recent breakthroughs, the stuff that's moving these incredible quantum ideas out of the isolated lab and into practical, scalable applications.
Right, moving beyond just cool experiments.
Exactly. You're going to discover how these photons are really set to transform, well, almost everything. From how we communicate securely to how we compute incredibly complex problems, and even how we measure the universe around us with accuracy we couldn't have dreamed up before.
We'll look at the amazing progress that's already been made
Mm.
and also touch on the exciting road that still lies ahead. There's still plenty to figure out.
Okay, let's start with a key concept then. You mentioned scalable. When we talk about scalable in quantum technology, especially with photons, what does that actually mean in practice? Because, scalable can sometimes feel like just a buzzword.
That's a really fair point, and it's fundamental, actually. What scalable means, it does vary quite a bit depending on the specific application. So for quantum communication, scalability means being able to send quantum information, like those secret keys, at high speeds over really long distances. Think coast to coast, or even globally.
Not just down the hall in the lab.
Exactly. And connecting many users into a robust network without the signal just, fizzling out or losing its quality. It's about building a true quantum internet, not just these short, isolated links.
Right, expanding the reach and capacity, making it a real network. That makes sense.
Precisely. Then for quantum metrology, that's the science of ultra-precise measurement scalability, is more about seamlessly integrating these quantum enhancements, these superpowers, into existing high-precision tools.
Ah, so making our current best tools even better, using quantum tricks.
You got it. Taking that super-sensitive quantum advantage and making it work reliably in real-world instruments, day in, day out.
And for quantum computing, that seems like the biggest scalability challenge.
Oh, it definitely is. For quantum computing, scalability means the ability to dramatically increase the number of quantum bits or qubits, maybe from tens or hundreds to thousands or millions eventually.
Wow.
And crucially, while doing that, keeping them stable and controllable enough so you can detect and even fix the errors that inevitably creep in. Quantum states are fragile.
Right, error correction is huge.
Absolutely huge.
Yeah.
This scaling and error correction, that's what's needed to unlock their true world-changing power. Without scalability, like you said, these amazing lab demonstrations would just stay as, well, scientific curiosities.
Okay, so scalability is key, and we're talking about needing incredibly precise light sources for this.
Huh.
Which brings us back to the core question, why photons? I mean, there are other ways people are trying to build quantum systems, superconducting circuits, trapped ions. What is it about these tiny packets of light? Why are they the ideal messengers, as it were, for this quantum revolution? Is it just speed?
It's a great question. And it's really a fascinating combination of things. Their mobility, yes, speed is part of it. They travel at the ultimate speed limit, right?
Light, yeah.
But it's also how little they interact with their environment. They don't easily get knocked off course or lose their delicate quantum properties, what we call decoherence.
Ah, so they keep their quantumness for longer while traveling.
Exactly. That makes them the natural, almost obvious choice for sending quantum information over distances. Perfect for quantum communication.
Mm.
But they're not just messengers. They're also vital for linking different quantum processors together, kind of like optical fibers in classical computing networks.
Okay.
And increasingly, they're being used as the core platform itself in many quantum computing designs. So they're doing the computing too.
So it really sounds like photons are kind of the backbone, the ultimate delivery service, and maybe even part of the processing engine for this whole quantum revolution.
That's a great way to put it. And to make this quantum future actually happen, the first thing we absolutely need are incredibly precise quantum light sources.
Right.
Think of them like highly specialized light bulbs, but instead of a steady glow, they can emit individual photons, one by one, or maybe specific pairs of photons that are quantumly linked, entangled exactly when we need them, and make sure each one is ideally identical to the last.
Okay, so consistency and on-demand delivery, what's the state of the art there? How good are we really at making these perfect little light packets?
Well, historically, a technique called spontaneous parametric down conversion, or SPDC, that's been the workhorse in quantum optics labs for years for making entangled photons.
SPDC, okay.
But it has limitations. Researchers like H.S. Zhang and his team over at the University of Science and Technology of China, they made a really significant leap. Back in 2018, they demonstrated what they called an optimal entangled photon source. And get this, they achieved 12 photon entanglement.
12 simultaneously. That sounds incredibly complex to manage.
It is. Generating not just one or two, but 12 entangled photons at once. That was a huge deal. It really signaled a massive step up in our ability to create the kind of complex multi-qubit systems you need for more advanced quantum computing and networking, moving beyond just simple proofs of principle towards, real power.
That really is scaling up complexity. What about making these sources smaller, more practical, like on a chip?
Great point. We've seen incredible progress there, too, on integrated chips. For instance, S. Pisani and colleagues, this was a big collaboration, including folks from the University of Bristol. They published work in 2020 using a different technique, spontaneous four-wave mixing, but doing it in integrated photonics right on a chip.
Okay.
And they achieved an on-chip single photon heralding efficiency of 91%.
Heralding efficiency, what does that mean?
Ah, good question. Heralding means the source creates photons in pairs. When you detect one photon of the pair, the herald, you know with high probability that its partner photon exists and is ready to be used. So 91% efficiency means when they detect the herald, they're very likely to actually have the single photon they want.
Got it. So it's a way to know you have a photon ready.
Exactly. And crucially, they also achieved very high indistinguishability, meaning each heralded photon was almost identical to the others. That's critical if you want photons to interfere properly in a quantum circuit, kind of like needing identical transistors for a classical chip. It gets us closer to reliable, mass-producible quantum light sources.
Reliability, consistency, integration. That sounds like the path to real applications. But what about getting photons truly on demand? Like, I press a button and I know a photon comes out, not just probably.
Right. Moving from probabilistic to deterministic, that's the holy grail for many applications. And that's where a clever technique called multiplexing comes in. Yeah, essentially you have several probabilistic sources firing at once. You check which one actually produced a photon, and then you quickly route that photon to the output. It transforms these maybe sources into something that's quasi-deterministic, much more likely to give you a photon when you ask.
Ah, like having several chances to succeed each time.
Kind of, yeah. In 2019, F. Kaneda and P.G. Quiet from the University of Illinois showed an efficiency of about 67% with high indistinguishability using this approach. And looking even further, more recently, X. Ding and a collaborative team, again including USTC folks, reported on a single quantum dot source.
Quantum dots, like tiny artificial atoms.
Exactly. And this source had remarkable properties. Purity of 98%, indistinguishability of 98%, and a system efficiency of 72%.
Wow, 98% purity and indistinguishability. That's incredibly close to perfect.
It really is. We're getting very, very close to that ideal photon-on-demand source, which just opens up so many possibilities.
Okay, give us a wow moment here. Just how good are we getting at manipulating the quantum properties of this light, the stuff that makes it so powerful for sensing, for example?
Okay, here's a real wow fact for you, related to sensing. Back in 2016, H. Valbrook and colleagues from Leibniz University, Hanover, demonstrated a record 15 decibels, 15 dibbles of squeezing strength for multiphotonic light sources.
15 dibbles of squeezing, what does that even mean?
Okay, can imagine light has this inherent quantum noise, like a faint static, that limits how precisely you can measure things with it. Squeezing light means you cleverly redistribute that noise. You reduce it, or squeeze it, in one property of the light, say its amplitude, at the cost of increasing it in another property, like its phase.
Ah, okay. So you make one aspect much quieter, much more precise.
Exactly. And 15 dibbles is a huge reduction in that quantum noise. It's like being able to turn down the static on a radio, not just a little bit, but dramatically, so you can suddenly hear the faintest signal much, much more clearly. This squeezed light is fundamental for pushing the limits of ultrasensitive measurements.
That's fascinating. So we can create these amazing quantum light packets with incredible precision. Let's see how we use them. Maybe the most immediate impact people think about is secure communication. Everyone worries about cybersecurity, right? From personal emails to national secrets, how do photons help lock things down?
Photons are absolutely critical for something called quantum key distribution, or QKD.
QKD, heard of it.
Right? It allows two parties, let's call them Alice and Bob, to create a shared secret cryptographic key. And the amazing part is, its security is guaranteed by the fundamental laws of quantum physics, not just by computational difficulty like most current encryption.
How does that work?
Well, basically, if an eavesdropper, let's call her Eve, tries to listen in on the quantum photons being exchanged to create the key, the very act of her measuring them inevitably disturbs their delicate quantum state.
Ah, the observer effect.
Precisely. Alice and Bob can then test for these disturbances. If they detect any sign of eavesdropping, they just discard the key and start over. There's literally no way for Eve to copy the key perfectly without revealing her presence. It's theoretically unbreakable.
So the act of spying itself makes the spying impossible without detection. That's brilliant. But how far can we actually send these unhackable keys in the real world? Are we talking lab distances or city to city or even further?
We're definitely moving towards longer distances and real-world networks. It's not just theory anymore. Back in 2018, Abe Oren and a team from the University of Geneva and ID Quantique, that's a company actually selling QKD systems, they achieved secure QKD over 421 kilometers of standard optical fiber.
400 kilometers. That's impressive through fiber.
It really is. But get this, a quantum communication backbone using QKD, stretching 2,000 kilometers from Beijing to Shanghai, has already been built and is operational.
2,000 kilometers.
Seriously. This was described by Y.A. Chen and collaborators from USTC in a major paper in 2021. This isn't just an experiment anymore. It's a real-world, large-scale quantum network in action.
Okay, that is genuinely real-world deployment. But optical fibers still lose signal over distance, right? Even 2,000 kilometers likely needs relay points. How do you extend that further, maybe across continents or oceans where fiber is impractical or just too lossy?
That is the challenge, and it's where a key concept called quantum repeaters comes in.
Quantum repeaters.
See, you can't just amplify quantum signal like you do with classical light and fiber optics. There's this fundamental rule in quantum mechanics called the no-cloning theorem. You can't make a perfect copy of an unknown quantum state.
So no simple amplifiers.
Exactly. So quantum repeaters work differently. They act like sophisticated relay stations. They divide the long, lossy channel into shorter segments. Then they use processes like entanglement swapping, linking entangled pairs across segments to effectively extend the reach of quantum communication without ever directly copying the fragile quantum information.
Wow, okay, that sounds complicated but powerful. How far along are we with building those?
It's still a major research challenge, but there's been amazing progress. In 2020, Yu and his team, also from USTC, achieved a really remarkable feat. They created quantum entanglement between two quantum memories separated by 50 kilometers of fiber.
50 kilometers between quantum memories. Okay, what exactly is a quantum memory here, and why is that 50 kilometers gap so significant?
Good question. A quantum memory is basically a device that can catch and hold onto a quantum state like the state of a photon for a little while without destroying it. Think of it like tiny RAM for quantum info.
Okay.
Achieving entanglement between memories 50 kilometers apart is huge because that's a core building block for a quantum repeater. It proves you can establish and maintain that essential quantum link over a meaningful distance, which is absolutely necessary for stitching together those longer segments in a future quantum network.
Got it. So repeaters for fiber. But what about truly global distances across oceans? Is there another way?
Absolutely. This is where satellites become a total game changer.
Satellites.
Okay, China's MISHIS satellite, which launched back in 2016, was a real pioneer here. It was specifically designed for quantum experiments. It enabled space-to-ground QKD over distances of 1,200 kilometers.
From space. Wow.
Yeah. And the MISHIS team, in a groundbreaking paper in 2017, they highlighted something incredible. This satellite link, just going through the atmosphere in a bit of space, achieved link efficiencies, how much signal gets through roughly 20 orders of magnitude higher than trying to send the same quantum signal through 1,200 kilometers of optical fiber.
Wait, 20 orders of magnitude.
Yeah.
I can barely comprehend that number. That's like a 1 with 20 zeros after it difference.
It's an absolutely astronomical difference. Basically, going through fiber that long, almost nothing quantum gets through. Going through space, much, much better. It shows satellites are a very promising route for global quantum communication.
That's just mind-boggling efficiency. What else did MISHIS do?
Well, it didn't just do QKD. It also successfully beamed down pairs of entangled photons to two different ground stations, 1,200 kilometers apart, and showed they stayed entangled. Yin and colleagues reported that in 2017.
Incredible, maintaining entanglement over that distance through the atmosphere.
And maybe even more spectacularly, in the same year, J.G. Wren and their team, using MICHAS again, demonstrated quantum teleportation. They teleported the quantum state of a photon from a ground station up to the satellite over 1,400 kilometers.
Teleportation, like Star Trek.
Well, not quite beaming people around. Quantum teleportation is about transferring a quantum state from one particle to another distant particle using entanglement without physically sending the first particle.
Yeah.
So, disembodied information transfer across continents and into space. It's not science fiction anymore. It's actually happening.
Okay, my mind is officially blown on the communication front. Photons as unhackable couriers, globally connected via satellites and maybe future repeaters. But what about computing? Can light particles really build a powerful quantum computer?
They absolutely can. It's another very active, very exciting area. One approach that's gained a lot of attention recently is called boson sampling.
Boson sampling. Sounds technical.
It is a bit, but the core idea is this. It's a specific type of computational problem that's believed to be incredibly hard for even the best classical supercomputers to solve, but relatively easy, in principle, for a photonic quantum device.
So a problem tailor-made to show off quantum advantage.
Exactly. Boson sampling isn't a universal quantum computer. It can't run any quantum algorithm like Shor's algorithm for factoring numbers. It's more like a highly specialized machine. But building one is seen as potentially easier than a full universal quantum computer, and demonstrating that it can outperform classical computers on this specific task, achieving quantum computational advantage, is a major milestone.
Okay, so who's pushing the boundaries here? Who's building these boson samplers?
The team led by H. Zhang and C.Y. Liu at the University of Science and Technology of China has been really dominant in this area. They built a series of photonic quantum devices named Juzhang.
Do you think?
Yes. And they've repeatedly claimed quantum computational advantage using a variant called Gaussian boson sampling. Juzhang 1.0, which they reported back in 2020, sampled photons from up to 76 output modes after they went through a complex interferometer with 100 modes, or paths.
Okay, 76 photons.
Then came Juzhang 2.0 in 2021. That scaled up to detecting 113 photons from 144 modes.
113 photons. Getting bigger.
And then, most recently, Juzhang 3.0, reported in 2023 by Y.H. Deng and the same group. This was a huge leap. They sampled an average of 255 photons from a system with 11,152 modes.
Wow, 255 photons being precisely controlled and measured as they interfere across over 1,000 possible paths. That's staggering complexity.
It really is. It involves incredibly sophisticated integrated photonic circuits and high-efficiency single-photon detectors. These are machines truly pushing the boundaries of what's computationally possible with light, performing sampling tasks calculated to be trillions of times faster than supercomputers could manage.
Are others building these too?
Yes, definitely. For example, another significant breakthrough came from L.S. Madsen and a large international collaboration, including the University of Copenhagen. Their photonic processor, called Borealis, demonstrated sampling from up to 219 photons in 216 modes, reported in 2022. So there's progress on multiple fronts.
Incredible machines. Okay, so we've covered communication and computing. You also mentioned metrology at the start, using photons for super-sensitive measurements. How exactly do photons help us measure things better?
Right, quantum metrology. We're talking about using quantum phenomena, like entanglement or that squeezed light we discussed earlier, to achieve exceptional accuracy in measurements, often surpassing the fundamental limits imposed by classical physics, what's called the standard quantum limit.
So it's like having a super-sensitive ruler powered by quantum mechanics.
That's a great analogy. A ruler that can detect the faintest disturbances or measure the most minute details far better than any classical ruler could.
And you mentioned an example earlier detecting gravitational waves, those incredibly faint ripples in spacetime from colliding black holes or neutron stars.
Exactly. That's one of the most stunning real-world applications so far. The Laser Interferometer Gravitational Wave Observatory, LIGO in the U.S., and the Virgo detector in Italy. These huge scientific instruments.
Yeah, amazing experiments.
They have actually implemented squeezed light injection routinely in their observing runs since 2019. This idea actually goes way back to theoretical work by Carlton Caves in the 1980s.
So they inject that special squeezed light into their kilometers-long laser arms?
Precisely. By injecting the squeezed light, these significantly reduce the quantum noise specifically, the quantum shot noise from the photons themselves, which was becoming a limiting factor for their sensitivity, especially at higher frequencies.
And what's the result? How much better are the measurements?
It leads to a really significant increase in sensitivity. They can hear fainter gravitational wave signals and signals from further away. The LIGO and Virgo collaborations reported in 2021 that this squeezed light boost has increased their detection rate of the weakest events, like binary neutron star mergers, by something like 20% to 50%.
Wow, so 20–50% more cosmic events detected just by using quantum light.
Exactly. And even the smaller but highly advanced GEO 600 detector in Germany reported achieving a factor of 4 increase in its signal-to-noise ratio using advanced squeezing techniques. It's really helping us open a clear window onto the universe.
That is just phenomenal, hearing the faintest whispers from cosmic collisions better. Are there other, maybe less cosmic applications of this super sensitive measurement, things closer to home?
Oh, absolutely. It's not just for gigantic astronomy projects. Remember that squeezed light can make measurements gentler, too.
Right, because you can get the same precision with less light, potentially less damaging light.
Exactly, and that's now being applied to imaging delicate biological samples at the microscopic level. A team including C.A. Casasio and others from the Niels Bohr Institute published a paper in 2021 showing the first demonstration of a quantum-enhanced nonlinear microscope.
Quantum microscope. Cool!
Yeah. They used squeezed light to image living yeast cells, and they achieved a 35% enhancement in the signal-to-noise ratio compared to using regular classical light.
Okay, 35% better clarity. Why is that so important?
Because, they calculated, to get that same image clarity using classical light, they would have needed to blast the cells with so much laser power that the optical heating would have damaged or even killed the live yeast cells.
So the quantum approach lets you see more clearly without frying the sample.
Precisely. It means we can now potentially peer into the delicate machinery of living biological systems with unprecedented clarity and gentleness. This could be revolutionary for medical diagnostics, for drug discovery, for fundamental biology, seeing things we simply couldn't see before without destroying what we were looking at.
That is truly incredible. What an amazing journey we've taken into this world of photonic quantum technologies, from unhackable communication spanning the globe to building these specialized quantum computers like Juzhang, and now peering gently into living cells and detecting ripples in space-time. It's clear photons are absolutely central to this revolution.
They really are. If we were to try and summarize maybe the key takeaways from our deep dive today, first, photons are pivotal. These simple particles of light, because they travel fast and don't interact much, they really are the natural choice for being the backbone of this quantum revolution, communication, computing, sensing. They play a role in all of it.
Right, the workhorse particle.
Second, scalability is accelerating.
Yeah.
This isn't just lab toys anymore. We're moving really fast from basic proof of principle demos to robust, complex systems that can be genuinely extended for real-world use. We saw that with the satellite QKD, the 2,000-kilometer network, and those massive boson sampling machines.
The progress seems incredibly rapid.
And third, real-world impact is already here. This isn't just promising future tech. Quantum photonics is already enhancing fields like gravitational wave detection with squeezed light and advanced biological microscopy. And many more applications feel like they're just around the corner.
It's truly remarkable when you step back and think about it. By learning to control these individual, fundamental particles of light with such incredible precision, scientists are literally building a future where our information could be fundamentally secure, our measurements impossibly precise, and our computing power could take this massive, almost unimaginable leap forward.
Absolutely. It makes you wonder, doesn't it? As we continue to get even better at controlling these photons, refining these techniques, what seemingly impossible challenges that we face today might these photonic quantum technologies help us overcome next?
That is the perfect question to leave us with. A lot to think about.